This is 4.3 part 2, talking about trig identities. So what we're doing today is just introducing these identities, and then in the future we're going to do quite a bit more work with these identities as we do more work with trigonometry. But before we start, when we talk about an identity, what are we talking about? What do we mean? If I say something's an identity, when we're in math, I say this is an identity. What does that mean? What are we talking about? Any ideas? No takers on identities? Identity is something that is true all the time. So an identity is something that's always true. So if we say an equation is an identity, it doesn't matter what we plug into the equation, it's always going to be true. It doesn't matter what the value of the variables are, it's always going to be true, no matter what. So that's what we mean when we're talking about identities. The first few we've talked a little bit about already, and we call these the reciprocal identities. So, and we used one or two during the homework. We talked about them. The cosecant of an angle. Oh, thank you. Just right there's fine. What function is the cosecant of an angle related to? Sine? So cosecant, we've said this before, was 1 over sine theta. The secant of an angle is related to cosine, so that's 1 over cosine theta, and the cotangent was related to the tangent. It's 1 over tangent theta. So we're just flipping our function over. And it works the other way around. If I take the reciprocal of this, then I turn this over. So I end up with sine theta is 1 over cosecant theta. Cosine theta is 1 over secant theta. And tangent theta is 1 over cotangent theta. So I can take the reciprocal, I can flip them over to get one from the other. So these we define these from the unit circle with 1 over y and 1 over x, and we know on the unit circle that y is sine theta and x is cosine theta. So to get all of these, they're reciprocals of each other. One of the reasons that we're worried about this, or that we're interested in this, is a lot of times when we work with trig functions, we get some combinations of functions. Cosecants, cosines, tangents, cotangents, and they're combined in various ways. We want to be able to simplify that by using these identities. So we end up sometimes with some kind of complicated equation, and we can simplify the equation by using these identities to make it a little easier to work with. So this is our first set of identities. The second set are called the quotient identities. And we've talked about one of these at least already. We said that the tangent of theta is sine theta over cosine theta. On the unit circle, the tangent is y over x. Y is a sine theta, y is sine theta, and x is cosine theta. And we know this reciprocal identity, so cotangent theta would just be the reciprocal of this, would just be the cosine of the angle over the sine of the angle. And I just want to mention here at this point, when we write our trig functions, it doesn't make any sense to write, for example, sine equals 1/2. It has to be sine of something. We have to have something in here. It could be an x, a theta, something. That's writing sine equals 1/2 is kind of like writing square root equals 1/2. There has to be something in there for it to make sense. It's something that happens a fair amount, so I just want to mention it. And you definitely don't want to make the mistake of saying that sine x over n, cancel out the n's and that equals 6. Can't do that. Just so you know. All right. So those are our quotient identities. Let's look a little more at this one and show you where this comes from our right triangle. So on a right triangle, we said, how do we find this? How do we find the sine of our angle if we have a triangle? Which sides do we use? Opposite over adjacent. So I'm going to write these, or opposite over, not the adjacent, but hypotenuse. We're talking about SOHCAHTOA here. And the cosine of the angle? Adjacent over hypotenuse. All right, so I'm going to write this fraction, just showing you how this comes from our triangle also. Write this fraction like so. So we get the tangent of theta, not tangent theta, sine theta divided by cosine theta. Is opposite over hypotenuse divided by adjacent over hypotenuse. And when I divide by a fraction, that's the same as multiplying by the reciprocal. And the hypotenuse in the numerator and denominator cancel out, and we get opposite over adjacent, which is tangent theta. So just showing you how this particular reciprocal identity or quotient identity comes out of SOHCAHTOA, comes out of when we use the sides of a triangle. And the other one is we just do the reciprocal. We're just turning it over. So that's where that one comes from with triangles. We talked about it with the unit circle. That's where it comes from our triangle. Questions before we move on? Okay. The last set, and this is probably the most important ones, the Pythagorean identities. This first one is probably the most important identity in all of trigonometry. Pythagorean identity, the first one, the primary one, says that sine squared theta plus cosine squared theta equals 1. And here when I'm writing sine squared, this is shorthand for sine of theta squared. So I'm squaring the whole thing. That's what this means. So this is our Pythagorean identity. We'll talk about where this comes from in two different ways. From this one, we can get two other identities. Our second Pythagorean identity is tangent squared theta plus 1 equals secant squared theta. And our third Pythagorean identity is 1 plus 1 plus cotangent squared theta equals cosecant squared theta. This one is the primary one. This one is the one that you will see the most often. And we'll talk about where this one comes from, and I'll show you how to get to these other two from this first one. So if you don't remember any others, remember this first one, and then I'll show you the trick to get to these other two if you forget these other two. All right, so let's look at our unit circle for this one. Let's look at our unit circle. Let me draw a circle up here. So here's our unit circle. Here's our center at 0, 0. And let me draw in a radius. On the unit circle, radius equals 1. What is the equation of a circle centered at 0, 0 with radius 1? Someone knows it. I'll get us started. X squared plus y squared equals 1. R squared. X squared plus y squared equals 1. That's the equation of that circle, centered at the origin. On the unit circle, x is cosine. Y is sine squared. So on the unit circle, sine squared theta plus cosine squared theta equals 1. So that's where this identity comes from on the unit circle. Now let's take a look at a triangle. Here's my triangle. Here's my right angle. Here's theta. Here's the opposite side. Here's the adjacent side. Here's the hypotenuse. What's our favorite equation? And our hint is in the title of this identity. What's our favorite equation on a right triangle? The Pythagorean theorem. So I'm going to write the Pythagorean theorem for this triangle. So I get the opposite side squared plus the adjacent side squared equals the hypotenuse squared. Now what I'm going to do here is divide both sides, everything on both sides of this equation by the hypotenuse squared. So I'm going to divide by hypotenuse squared, divide by hypotenuse squared, and divide by hypotenuse squared. Hypotenuse squared divided by hypotenuse squared is 1. Opposite over hypotenuse on my triangle. Sine. This is sine squared theta. Opposite over adjacent over hypotenuse. Cosine squared theta equals 1. So this comes from the Pythagorean identity. Is called the Pythagorean identity because it comes from the Pythagorean theorem. We apply the Pythagorean theorem to this triangle and we get this identity. The equation of the circle comes from the Pythagorean theorem also. So that's why they're similar. So this is our main Pythagorean identity. I want to show you how to get to the second one from the first one, and then you'll see how to get to the third one. So a lot of times I won't necessarily remember exactly how these work, but I know this one. So now from here, I'm going to do this in red. I'm going to divide everything in this equation by cosine squared. I'm going to divide everything on that equation by cosine squared theta. And sine theta over cosine theta is tangent theta. Tangent squared theta. Cosine squared theta over cosine squared theta, 1. 1 over cosine theta, secant. So that's how I get to the second one from the first one. So if you can't remember the second one, how it works, just remember you start with sine squared theta plus cosine squared theta equals 1, and divide everything by cosine squared theta. If I do the same thing, if I go through this equation and divide everything by sine squared theta rather than cosine squared theta, I would end up with this identity. So all three of these identities come from the Pythagorean theorem, and these other two actually come from this first one. Questions on that? Okay, let's take a look at how we're going to use this. So a couple of ways. Today we're just kind of dipping our toes in, simplifying some equations or using these identities to get to answers that would otherwise we'd have to go about a different way. But combinations of trig functions show up a lot when we use trig functions in applications, when we're solving problems with trig functions. And if we can simplify them using these identities, that makes our lives a lot easier. So that's really the main reason that we're going to do this. So let's look at this first example. We know that cosine theta is 0.3. And we want to find the exact value of sine theta using identities. So before we start on this particular problem, if we didn't have to use identities, if it just said find the sine, if the cosine of theta is 0.3, find the sine of theta, how could we go about that? What could we do using something that we already know? Anybody have an idea? What would we do, or what did we do in our last lesson when we came up with an answer that said cosine theta equals 0.3 and we needed to find theta? What did we do? Inverse, not the sine, but the inverse cosine. So if we did the inverse cosine of 0.3, that would give us our angle. Then how would we find the sine of the angle? Plug it in our calculator, right? So we could use the inverse cosine to find the angle and then take the sine of that angle to find the sine of the angle. So that's one way we could do it if we didn't have to use identities, if we didn't want to find the exact value. Well, we're going to find the exact value using identities. We have a Pythagorean identity that relates sine and cosine. We know that sine squared theta plus cosine squared theta equals 1. So sine squared theta plus 0.3 squared equals 1. And I can subtract 0.3 squared from both sides. 1 minus 0.3 squared. Now we want an exact value, so how can I write, instead of writing 0.3 as a decimal, what's another way I could write 0.3? Well, if it was 0.3333 repeating, it'd be 1/3. What's another way of writing 0.3? 3/10. So I'm going to say sine squared theta equals 1 minus 3/10 squared. So that equals 1 minus 9/100ths. 1 minus 9 100ths is what? As a fraction. 91. 1 is 100 hundredths. So subtract 9, I get 91 100ths. And now I can find sine theta. Sine theta equals the square root of 91 over 100. And I can rewrite that as square root of 91 over 10. So there's my exact value of sine theta, knowing that cosine theta is 0.3 or 3/10. Now once I have this, could I now then go on and find the exact value of all 6 of the trig functions? Because I have sine and cosine, I can find tangent. I have the cosine, so I can find the secant, the reciprocal. I have the sine, so I can find the cosecant, the reciprocal. So I can find the exact value of all 6 of the trig functions from here. That's one benefit of using identities. We get this exact value, and then I can find the exact value of all 6 of the trig functions for this particular angle. So that's one example of how we would use this identity. Questions? Everybody clear on what we did there? All right. On your homework, there are several problems, numbers 59 through 66, where it asks you to show that you can transform one side of an equation into another side of the equation using identities. So I just want to do a couple of examples of those kinds of problems. So one question might say, show that cosine theta times secant theta equals 1. We want to show that this is true. So what I'm going to do is use my identities to rewrite these. My suggestion for these problems is start by writing everything just in terms of sines and cosines. So I'm going to say we're going to leave this as cosine theta. We have an identity for secant theta. How can we rewrite secant theta? 1 over cosine theta. Well, cosine theta times 1 over cosine theta, cosine theta divided by cosine theta equals 1. So that's how we show we can take this side of the equation and make it equal 1. So we're not working across the equal sign. We're showing that we can change this into this. So let's look at one more. Cotangent theta times sine theta. We want to show that that is equal to the cosine of theta. We want to show that we can change this into this. We can rewrite cotangent theta as cosine theta over sine theta, and we're multiplying that by sine theta. Now I have the sine theta in the numerator and sine theta in the denominator. Those cancel, and this just equals cosine theta. So you'll do a few of these problems, 59 through 66, in your homework that ask you to show that using identities that you can get from one side, transform one side of the equation into the other side. And this is the kind of thing you're going to do. There are a couple that are a little more involved than these two, but we're just using our identities and getting from one side of the equation, showing that we can turn it into the other side. All right, questions? There's our first little introduction into identities. Let me put the homework up, and then we have a lab that we're going to do in class today. All right, so a lot of these at the beginning are just calculator or remembering that secant of theta is 1 over cosine, that kind of thing. The 59 through 71 odd are the ones where you're using your identities, and these are more right triangles. All right.